I usually run this, this talk should run about 30 minutes, which means I'm going to talk kind of fast. Who listens to podcasts at like 1.5 times? Yeah, most people. Cool, so you'll be very familiar. All right, I'm gonna talk kind of fast. This is the evolution of API design. Before I start, I want to say thank you to all of the organizers. Putting on an event like this is a ton of work. It's really hard. Thank you to all of the sponsors and to the volunteers who make it possible. So, okay. Today, I am going to try and talk about some buzzwords, and I am going to hopefully add a little bit of context, and maybe you'll come away knowing how some of the buzzwords could be useful in real life. Quick intro, I'm Eric. I work at Formidable in Seattle. We build generally really big JavaScript things, but we do all kinds of stuff. I'm going to keep going. Gotta be quick. Okay, so the first thing is I want to address kind of the elephant in the room when it comes to GraphQL. I'll start by saying, new things, they're always really exciting, but somewhere in the back of your mind, you may be thinking, why do I need more tooling? Or why do I care? REST is fine. And it's legitimate. And the reason you should care is that the benefits of any new tool or tech have to be weighed against the cost to bring it into a system. There are a bunch of ways to measure the cost. There's the time to learn, the time that it takes to convert what you have, the overhead of maintaining two systems at the same time during the rollout. And with the high cost, something has to be better or faster by kind of a huge amount to be worthwhile. Incremental improvements are really fun. They're fun to talk about and for side projects, but usually they're not worth the investment for substantial development. So the things I want to talk about today, GraphQL in particular, they are, in my opinion, a huge step forward and more than enough to justify that cost. Okay, so to understand why these tools exist, oh no, I didn't start my timer. To understand why these tools exist and what makes them great, I want to talk a little bit about APIs in general and the trade-offs in the designs that got us to where we are today. So we'll start with kind of going back in time. And the first stop is the mid-60s, and I was looking up some history to prep for the talk, just some stuff about the 60s, and I found the most useless thing on all of Wikipedia, because it has a citation, and it's still there, and you should look because it's amazing that it exists. Wikipedia is great, community. Okay, so in the 60s, computers were big enough and they were expensive enough that API-driven development, the way we think of it now and kind of take for granted, was mostly theoretical. So because of bandwidth or computation or other performance constraints, most APIs were just a mechanism to run code on a remote computer. There weren't contracts, kind of how we think of them now. So with the 60s, or with ARPANET in the 60s, all the way up into the mid-90s with Corba and RMI and some other things, a lot of computers interacted with each other using remote procedure calls, which is client-server interaction model where a client causes a procedure or a method to execute on a remote server. And by the way, we talk now about RPC as sort of just these named methods, but this is what it actually is. Okay. So there were, and there really still are, a lot of good things going for RPC. The ability to treat a remote environment as if it were a local one, albeit slower and less reliable, can create a continuity to distinct and disparate systems. And like a lot of things from ARPANET, it was way ahead of its time. I mean, since then there's been a tremendous amount of research into how to embed asynchronous and unreliable behaviors into a normal control flow. And if things like promises or futures or scheduled tasks or whatever sort of primitive for that, in any given language had been around at the time, our API landscape may look very different. But there are a lot of difficulties with RPC. I mean, the first is that with continuity comes context, right? And what I mean is that RPC by design creates coupling between local and remote systems. You lose the boundaries between your local and remote code. And for some domains, this is okay or even good, but it's considerably less flexible than something that is purely data-driven. More important is the proliferation of API methods. In theory, you always start out with a small, thoughtful, API surface, and then, it's a real project, and you start bolting on methods. This can be especially problematic when, over the lifetime of a project, you change names for something, right? User becomes customer, or something like that, and you have all kinds of duplication. Sure, some of this could have been solved with documentation, but we don't even have that now. So, okay, so the next thing to come along really was SOAP, or at least the next big kind of trend. And this was born in the late 90s at Microsoft Research. It was intended to address some of the practical drawbacks of RPC by adding structure to APIs. It was actually sort of a competitor to XML RPC. It's a really interesting story. There's some good blog posts about the history of SOAP and how it happened. Anyway, SOAP is a messaging protocol for exchanging structured information. It tries to be cross-platform and extensible, and it was among the early moves in the direction of resource-oriented APIs. So using a SOAP endpoint, you request data of a predetermined shape rather than think about the methods that are required to generate the data. SOAP is flexible, so there's that doesn't always happen, but that was kind of some of the idea. SOAP 2, it had some good things going for it, despite its sort of unbearable verbosity. It started to move away from procedural APIs and towards a more declarative data model. The contracts ensured predictable results. Client-server contracts are a good thing. And it had the ability to auto-generate documentation and integrate with some IDEs. The big revelation of SOAP, though, was that it was more resource-oriented. It sort of started to move in that direction, and it had guaranteed client-server contracts. The downside is that it was sort of impossible to use without tools. You need special tools to write tests and special tools to inspect responses and so on and so on. And it was, I mean, if you've ever worked with it, it was pretty horrible. It was possible that was just a part of the Microsoft strategy of the 90s. But, you know, it's still used in a lot of older systems, but the hard requirement of tooling makes it cumbersome, and the number of bytes you need for XML makes it kind of a poor choice for chatty networks today. And by the way, when I say a lot of tooling, it is just XML, but it's very verbose. And if you've ever tried to like debug XML in like that little toolbar at the bottom, it's not fun. Okay, so the latest design pattern is REST. REST was introduced in a doctoral dissertation by Roy Fielding in 2000, and it swung the pendulum in a fully different direction. So REST is, in a lot of ways, the antithesis of SOAP. And when you look at them side by side, it feels like his dissertation was like, it was a rage quit. And so I reached out to UC Irvine and Dr. Fielding's alma mater, and they shared some footage of him working with a SOAP endpoint right before he met with his advisor to talk about REST. So this is Fielding working with SOAP. So SOAP used HTTP as a dumb transport and built all this structure and the request and the response. REST threw out the contracts, threw out the tooling, threw out the XML, the bespoke headers. It replaced it all with just HTTP semantics as its structure. And it uses standard verbs, get, put, post, to fetch and update data. URIs are a reference to a resource. REST changes the thinking from modeling interactions to and programming with remote services to just modeling the data of a domain. So in other words, REST is fully resource-oriented, and you don't have to know or care what it takes to generate that resource, usually. So it's simple compared to what came before it. It's easily cacheable. It's simple to scale because it's supposedly stateless if you do it right. You know, since it models the data instead of anticipating needs, it should reduce the API surface. But you know, REST, like all of the silver bullets that have come before it, is not without its flaws. And to talk concretely about its shortcomings, I'm going to kind of just do a quick example, something for this to stick to. And I'm going to use this as a reference point for the rest of the talk. So let's pretend we have to build the landing page of a blog, which just displays a list of posts and their author's name. Now, first, we're going to fetch our list of posts from our post endpoint. Our API would return a list of posts and the URI required to fetch the additional information for each one. Alternatively, in the world, real world, your API might return a list of IDs that have to be concatenated onto a URL that you have to find from Confluence. But next, we'll fetch the data about each of the posts. And then after that, we'll have to fetch the author for each of the posts. So now we have all we need, and it's really well organized. It's easy to reason about, but it took us 8 API calls to get there. And so the ergonomics of developing REST it's certainly better than what came before it, but a lot has changed since Fielding's paper. That was 2 decades ago. I mean, at the time it was a period of exuberance, right? It was the explosion of personal computing. Every year, computing speed was doubling. You could get more memory in your device. Networks were getting faster and faster. I mean, Moore's law became a household name at that point in time, right? And then mobile computing came along, and we immediately regressed a decade, right? right? So the expectations that we, well, I mean, in terms of our capabilities, right? So our expectations about what about our network are not quite as we can't be as exuberant as we used to be. So which brings me to REST's three main weaknesses. REST is very chatty, it returns way too much data, and it lacks any mechanisms for introspection, right? So first and foremost, the thing I want to point to is that REST services tend to be chatty. And what I mean is that it generally takes a whole, oh, thank you very much. It takes a whole lot of back and forth between the client server to get all the data you need. And the performance of implications of that can be devastating. So maybe you're skeptics, maybe you said, whatever, I watched, you know, House of Cards on my commute, and like, I'm not Alex Russell and I can't do all the performance things, but like, I'm gonna try and quantify what I mean by the performance impact. I mean, they are substantial, but I'm not gonna just leave it at that. So the first problem is latency, which is the amount of time it takes for data to move through a network. So whether you're sending a gigabyte or a byte, this is constant for a given network type, or near constant. So for wired networks, we're talking about electrons through copper, maybe light through fiber. For mobile networks, things get considerably more complicated, so unsurprisingly, it's a bit higher. The latency for today's fastest 4G network is still triple that of a wired connection, and 3G, which covers most of the world, has latency an order of magnitude higher than wired. So the important thing to know is that this latency overhead is for every request, and that no amount of technology, kind of, sorta, can overcome that fact, right? So for mobile, we can kind of get it down because we can remove complexity in the system, but latency is constant, right? So to think back to our example blog, if you take those latency numbers and you imagine a best case scenario, you have a new phone, a reliable network, you know, no subways, a 4G connection, you've spent a half a second, which you know, of your performance budget, which is a reasonable percentage of like you know, what should be a performance budget, on just pure overhead. This is before you've even downloaded your first byte. This is before you've rendered anything to your app or your website or you know, whatever your client is. And these numbers, you know, they don't account for your server performance either, right? This is pure overhead. So by the way, I will acknowledge that HTTP2, or sometimes just H2, has the potential to alleviate some of this burden. I don't have time to get into it, but let's come chat afterwards. We'll talk about H2. It's really cool stuff. Even so, even if H2 completely got rid of the question of chattiness, you still have a different problem here, and that is that something that has nothing to do with HTTP, and that's it has to do with TCP itself, which is the protocol that underpins HTTP. The long and short of the problem is that all connections are made over an asymmetrical network. So a data center will obviously have a much higher bandwidth connection than your mobile device, and if a server were to send data at 100% of its capacity right away, the device would be overloaded. So TCP does something called slow start, and slow start, you don't really need to worry about the graph other than just sort of its general shape. The implication is that one big request is often much, much faster than smaller ones because it spends more time downloading data at the network's maximum capacity. And the last piece of why this matters, I'm not going to get into too much for time reasons, but it has to do with how radios work. Basically, the battery is one of the most intensive, or sorry, the radio is one of the most battery intensive parts of the phone, and so your phone is always trying to turn that off. So you get more overhead by constantly initiating all these requests. Okay, so the next problem with REST is that it sends more information than you need. So API authors have to kind of anticipate all use cases, and more often than not, they'll send a complete resource regardless of whether or not their client needs it. So in our blog example, all we need is the title and author, and this is all the stuff we get back. And that ends up being about 17% of this, which is a 6x loss. And this is sort of a made-up example. But in the real world, I mean, I've been in situations where I have a 95% of the data is wasted, right? I'm going to just move on from that one. The final thing is that REST lacks any mechanism for introspection. I'm not going to get into the details, but without a real contract, without some type safety, without some specification around what's going on, there's no way to generate documentation reliably or create tooling or help developers explore or interact with the data like there was with a WSDL model when they worked. And you know, to be honest, like sure, you can do a lot of this stuff with REST, but I can probably count on one hand the number of times I've interacted with a REST API that had impeccable documentation and perfect tooling, you know, perfectly implemented, you know, Swagger spec and that whole thing. So there's the theoretical and then there's the reality. That's kind of how I see it. Okay. So there are, of course, a lot of people trying to solve these types of problems, and in a lot of different ways. And so some people have ended up writing custom endpoints. Some people use OData, JSON API. There's a bunch of things that kind of help you get a grip on REST, and they're all really thoughtful standards, but they're kind of bolted on top. So, maybe with an understanding of both the things that have worked and not worked in the past, we can try and figure out what's the new foundation. Like, what would we rather have, instead of trying to bolt on to the existing stuff. So given today's constraints and 2 decades of research, languages that are more powerful, and today's constraints around mobile, so let's sketch out the API that we would actually want. So we know that we would want minimal HTTP traffic. Right, so there's serious overhead with network requests from latency or battery issues or any number of things. We want to reduce that to as few as possible. But we also know that the average client is resource constrained, right? So this could be memory, this could be CPU, bandwidth. I mean, there are all kinds of constraints on our clients. We should probably try and send only the information the client needs. So we need a mechanism for the client to ask for the data that it needs rather than having API designers try and anticipate and just sort of push, right? We need a pull, not a push. We would like for it to be human readable, right? We learned from SOAP that even with all the great things that it may offer, we still want to use curl and wget and fetch and Chrome and Postman and all these things that we're sort of used to. But on the flip side of that is that we do still want tooling, right? We don't want to have to use tooling, but we want the ability to wrap our APIs in good tools. The final one, which is something that people don't talk about all that much, is the ability to preserve local reasoning. So over the years, we've developed a lot of ways to organize our code bases. Every project's a little different, but for the most part, we do it around the idea of cohesion, right? So things that are related all go in the same area. And it would be really nice if we could extend that cohesion or the encapsulation or separation of concerns or however you want to phrase it, if we could extend that to our data layer, right? So right now, most apps are built, we have all these really nice abstractions, and then we have the data blob that everything connects to, right? It would be nice if we could preserve local reasoning. Oh, sorry, animations are fun. Okay, so what would that look like? So if we imagine how we might fetch data in our blog example, on the right, it is the right. Yeah, it's the right for you guys. We describe the data that we need in a format that looks similar to JSON, kind of like what we'd want to get back. It's nice and readable. And the query says we want posts, and from each post, we want the title and we want the author's name. And if I send that to the server, I might get something like this back, which is just a list of posts with the data that we requested. And if this were possible, it would fulfill at least some of these things. So we would have minimal payloads, since we're able to convert our 8 previous requests into 1. And it also fulfills our need for minimal traffic. But modularity and local reasoning, not so much, right? So we still have these big queries that just represent everything our app could need. If our blog has sort of an author component or area or feature and a post set of code requesting all the data at once, we still have multiple things depending on one data blob. So if we could break it up, right? We could give each component only the data that it needs to render, and we might have something like this. But now we're back to breaking that whole minimal HTTP thing, right? Now we could, in any sort of mobile application, we could have hundreds of data back components, and this would probably be a regression. We can fix this, though, if we can merge those two things into one. And this can be accomplished really easily if we use a query language that can be easily parsed in conjunction with a known schema. And in fact, if we could do that, there's a lot of really interesting things that you could do. So you could intercept all requests, and similar to how we could create an abstraction layer that batches requests for data, right? We could use a compiler to extract requests and pre-cache the data. There are a lot of things you can do when the requests to your server are machine readable, right? So I touched on this a little bit on the last slide, but the last thing on our list was tooling. Something that earlier protocols got right was allowing the server to publish a schema that defines the data. And by using strongly typed schemas, tools can do static analysis or integrate with IDEs or do query validation or all sorts of things that you don't want to run into at runtime. And so now I get to tell you that I lied a little bit. And the lie is that these APIs in various forms have been emerging all over the place. So there's something called Meteor that did some of these things. There is something that came out of RethinkDB, rest in peace, that launched that did some of these things. Netflix has a tool called Falcor that does a lot of these things. And then there is Facebook's GraphQL, which is what I actually use to model the sort of dream API, right? And I love the simplicity of Falcor, but it is impossible to overlook GraphQL's dominance in developer mindshare. So for the rest of the presentation, I'll focus on GraphQL and its semantics. And since GraphQL, since I can't really imagine anything better than their homepage, I'm just going to kind of plagiarize it. So this is the example that they have on their homepage. I actually think they changed the colors around a little bit since I made this slide. But so in GraphQL, you describe the data as a graph of interconnections, and you ask your client specifically for the data that it needs. And the GraphQL returns data of the same shape. Or sorry, the server returns data of the same shape. So I'm not going to do a demo today. I have one, and I would love to show any of you if you're curious about GraphQL very specifically, right? So this is the arc of like why GraphQL came to be and why it's important. I sort of see it as sort of a next step, and if not GraphQL, then something very, very similar to it. So come find me if you're curious. But before I kind of go, I do want to mention a few of GraphQL's more interesting properties that you should think about before you decide to pursue it. So the first thing is that GraphQL is a spec, and it is not an implementation, right? And that spec defines a type system and a query language, and that is it. Right? So there are implementations in over 24 languages. The reference implementation, which is actually kind of crappy, is in JavaScript. Python, the graphene library is pretty good. There's Sangria in Clojure. There's one in Ruby. I mean, I think there's one for every single language, right? The other thing is that it's a spec that implements just a type system and a query language, and I didn't say anything about data, right? So GraphQL is completely agnostic to its data source. GraphQL just stitches together a whole bunch of requests, and it lets you fire off external functions to figure out how you're fetching that data. So that could be a SQL query, but you could also fetch data from Redis or an internal API or something in memory or some other thing. And actually, having worked with GraphQL for a while, this sort of orchestration layer, right? So fetching data from a bunch of disparate sources, internal and external, and then stitching them together into something that is usable for the next layer in your stack. This is something that I've done in almost every software project I've ever been on. So I've been on projects, they call it a DAO, they call it an orchestration layer, anything like that. So this is a generalization of that idea, right? So the next is GraphQL's progressive disclosure of complexity. GraphQL does a fantastic job of making the simple things simple, and the hard things also are possible, right? So this slide is a perfect example. You can get immediate use and feedback from a GraphQL server. It's pretty straightforward, but you can also and you can sort of layer it on top of an existing REST API, or you can do field level authentication, and you can map complex data models, and you can do subscriptions and all sorts of really advanced stuff. So projects sometimes struggle to find that nice balance. Some projects are easy to learn and hard later, and some projects are just impossible to learn, but then once you get the hang of it, anyway. So the last and most important is that a GraphQL server publishes what's possible and lets clients decide how to use it. So this stands in pretty stark opposition to publishing just a pile of resources and saying, hey, clients, run a join over this, right? So this client-server contract thing is really nice, so keep that in mind. So before I close out, this is my last slide. I want to say I believe the hype is justified, but there is no silver bullet. GraphQL is great, but it's not without flaws. It is a tool that seems purpose-built for good data. Facebook may have immaculate APIs. I don't. Complex data can be difficult, right? Another thing is that because GraphQL stitches together so many different services, you can end up with partial data. Now, of course, you can set it up so that it fails if any part of the query fails, but figuring out how to do error handling can be challenging. Analytics and monitoring is still catching up. Anyway, I think that GraphQL is something absolutely worth exploring for a lot of different problem sets, but I don't want anyone coming away trying to, thinking I'm trying to make a pitch. And actually, if you come talk to me, I will tell you all of the horror stories about implementation. It can get ugly from time to time, just like any project. Okay, so I spent most of the time talking about why GraphQL exists and the problems that it solves, its actual semantics and uses. If I've piqued your interest, go out and learn in whatever way works best for you, whether it's blogs or YouTube or reading the source. That's all I have time to share, and I hope that at least a few of you will go explore it. And I've been working on this in production for a little while, so come ask questions if you have them. Follow me on Twitter. I usually hang out trying to help people get started. So that's it. Thanks, everyone.